Welcome back to Integral Calculus. In this video, we're going to take an overview of elementary integration rules. At this point in your study of calculus, you've learned a number of different rules for integration. The power rule, use substitution, certainly, integration of all of the trigonometric functions, integrals that result in logarithms, integrals of exponentials, and integrals that result in inverse trigonometric functions. There's enough going on at this point that it can sometimes be a little bit tricky to figure out which approach is the best for the problem at hand. That's exactly what I want to address in this video. Let me get my head out of the way, and I'm going to start with a couple of very basic the integral of dx over x plus 16, the integral of dx over x squared plus 16, and the integral of x dx over x squared plus 16. These three integrals look incredibly similar, but to a trained eye, the differences become immediately obvious and also immediately show how to approach the situation. In the first integral, because that denominator is linear, I know that I don't even need to bother writing out the substitution, but I'll go ahead and do it anyway. Let u equal x plus 16, then du is equal to dx, and this becomes the integral of du over u. The integral of du over u is the natural log of the absolute value of u plus some constant of integration. I should probably put that on a new line instead of trying to go across the page so that I have enough room for all of the other integrals here. And then substitute back in the meaning of u. This is the natural log of the absolute value of x plus 16 plus our arbitrary constant of integration. If I tried that same approach with the next integral, then I'd have that du is equal to 2x dx. And I'd realize immediately that I have a problem, because I have no way of getting that 2x up here with the dx in the numerator. All right, so that approach is out, and we want to find something else. If I was doing this pencil and paper, I would just put a thin line through it to remind myself that I tried that, because you're probably going to try a couple of different things, and that way you don't end up in a circular path where you're retreading the same ground over and over again. But that's not where I am. I am looking at something different. So let's try something different. Maybe after a little bit of thought, I recognize, well, what if I wrote that 16 as 4 squared? And then what if, even more than that, I wrote the terms in the denominator in the other order? All of a sudden, that looks like an integral that results in arctangent. All right, so coming off of that result with arctangent, maybe I'm looking at this third one. I'm looking at that denominator, realizing it's the same thing, and thinking about trying the same approach. But if I try that, I realize there's an extra x in the numerator, and that extra x in the numerator is just going to get in the way. And then I remember what went wrong in the last one when I tried the substitution, let u equal x squared plus 16. I couldn't figure out how to get the x with the dx. But in this case, it's already there. I just need to introduce a 2, which I can do by putting a 1/2 in front. So I have 1/2 the integral of du over u, which is going to be 1/2 times the natural log of the absolute value of u plus c, and then substituting back in. Oh, great. I'm so low on the tablet that I can't get my pen to mark out. Luckily, I can scroll. And technically, I'm done with that. 1/2 times the natural log of the absolute value of x squared plus 16 plus our constant of integration. But I can take this 2 steps further, and there are some reasons I might want to. The first one, I think, is something that as a student I never took the time to think about, but it's a good habit to get into. Those absolute value bars are doing nothing. I can make them go away. Well, why? I can put any number I want for x, positive, negative, or 0. When I square it, I'm going to get a positive number. If I have a positive number and I add 16 to that, I'm going to have an even bigger positive number. The absolute value of a positive number is the number you started with. So the absolute value bars aren't doing anything here. That's a trick that is very often used when you're checking answers in the back of a book. And it's one that often confuses students because, wait, there were absolute value bars, now there aren't. I have absolute value bars in this one and not in that one. What's the difference? The difference is we can often make that argument. And then one more step. Again, if you don't do this on an exam for me, I'm not even going to notice. But it's a nifty trick that often confuses students when they're checking answers in the back of a book. We have that 1/2 in front. Properties of logarithms say I can use that and write it as x squared plus 16 to the 1/2 power, and the 1/2 power is a square root. I'm fairly certain that I talked about those ideas in the video on integrals resulting in natural logarithms, but just in case I haven't, or in case you kind of glossed over it, I thought it was worth repeating. Those are the things that, as a student, drove me absolutely up a wall. Trying problems out of a textbook to get some practice, checking my answers in the back of the book, seeing a different result, and not realizing that it's the same result written differently. So whenever I can, I like to show tricks and tips on how textbook authors can rearrange their solution in a way that looks nicer to them and makes them happy. All right. Anyway, moving along. A colleague showed me this integral a couple of years ago, and I have become somewhat obsessed with it because it works so beautifully. The integral of dx over 1 plus e to the x. The reason I like this integral is it involves the trick of creating something out of nothing. It would be really nice if I had an e to the x in the numerator. And I can make that happen. I added and subtracted e to the x in the numerator at the same time. Why did I do that? Well, originally I had addition in the denominator of the fraction, which meant I couldn't really do anything. But now I have addition in the numerator of the fraction, which means I can split this fraction up. Specifically, I'm going to split it up over that bit of subtraction there, and I'm going to break it into two separate integrals. So I have the integral of 1 plus e to the x over 1 plus e to the x dx, and then I'm subtracting the integral of e to the x over 1 plus e to the x dx. In the first integral, I have the same thing in the numerator and denominator. Those go away. In the second integral, I can do a u substitution. Let u equal 1 plus e to the x. du is going to be e to the x dx. And that e to the x is the reason I couldn't just jump in with a u substitution in the first place. I needed to have the e to the x with the dx there in order to make the substitution work. Integral of dx is x. Integral du over u is the natural log of the absolute value of u. And then substitute back in the meaning of u. And even though I have natural log and exponential hanging out so close to each other, the extra 1 plus in there means that I can't do anything to cancel things out. How about one more to stretch your mind a little bit? The integral of 1 plus the natural log of x over x. This is kind of strange because the complication is in the numerator. The first time I saw this, my immediate reaction was to split up the numerator and make it two fractions, and that absolutely does work. But you don't really need to. It's kind of strange, and it's not something we see all that often. But look at what happens if you set u equal to the numerator of this fraction. Well, the derivative of 1 is 0. The derivative of natural log of x is 1 over x. And this integral is just the integral of u du, which comes out as 1/2 u squared, plus your constant of integration. Plug in the meaning of u, which I am writing too big to fit on the screen. All right, tighten this up a little bit so I have a little bit more space. 1/2 times 1 plus the natural log of x, the whole thing squared, plus our constant of integration. All right, so a couple of different ways of looking at things. I hope that your biggest takeaway from all of this is that integration is more of an art than a science. Looking at the integrals you're trying to work with and finding a way to go through the process is going to be a process of trial and error. You're going to make mistakes. You're going to take false turns. Realize that what you have done isn't working. Stop, regroup, try again. With practice, you start to notice patterns and you can more easily recognize what's happening in a particular expression and use it to your advantage. I think that's everything I have on this one. Nothing new here, just a whole bunch of same old in ways that you've never thought of before. Let's wrap up with one for you to try. How about the integral of 2x dx over the square root of 4 minus x squared? All right, take a couple of minutes, see what you come up with on that one, and I'll see you in the next video.